So we're doing 7.1 today. This is graphing exponential growth functions. I really don't think this section is that difficult. You just are going to be exposed to a new formula, a couple of new rules, and a new graph basically. But going right into the vocabulary of this, we talked about, already said, exponential functions. So an exponential function has the form of y equals ab to the x. So that's a times b to the x. Remember, we cannot multiply a times b because b has to be taken to the x power first. That's our order of operations. So we'll always show the form of a times b to the x, where x is not equal to 0 and the base b is a positive number other than 1. And then it says if a is greater than 0 and b is greater than 1, then the function y equals a times b to the x is an exponential growth function. Okay, so if a is greater than 0 and b is greater than 1, then we're going to have a growing function. Okay, and b will be called the growth factor. The simplest type of exponential growth function has the form y equals b times x. So that's when there's nothing being multiplied by the b in front of it. Okay, so a and b will both be integers or numbers typically, but the idea of this is that now your variable is up in your exponent. So let's talk about the parent function. So we've talked a little bit about parent functions in the last chapter. So that is b to the x. And basically what this function looks like is this. It's an exponential growth, which means it's starting really small and then it grows rapidly, especially after we get into the x positive. So your starting point, you can see, is 0, 1. So that's when we have b to the x. Okay, if it's just b to the x, then our starting point will be 0, 1. That's our y-intercept. How do we know that? Well, if we plug 0 in for x, we will get 1 no matter what b is. And then our first point after that we usually plot is going to be 1, and then it'll be whatever our b is. Okay, and again, that's with our parent function. So if our b is 4, then that means it's going to be 1, 4. If our b is 3, it's going to be 1, 3. So that's going to give us an idea of what our function looks like, because again, an exponential function looks the same every single time. So right here it says the graph rises from left to right, passing through the points 0, 1 and 1, b. Now, the one other thing that I want to note over here is it says the x-axis is an asymptote. We used this term a little bit in the last chapter. And what an asymptote is it's a line that a graph approaches but never touches. So in this case, the asymptote is the x-axis, which means our graph will continue to get closer and closer to the x-axis, but it will never touch it. And that'll be a little bit important as we move forward. Okay, so that's the asymptote, is the x-axis, and that's of the parent function. The domain of this will be all real numbers. The domain of any exponential function is going to be all real numbers unless you start dealing with square roots and things like that. The range, again, because it's approaching the x-axis, but it never hits it and it never goes below it, it's going to be y is greater than 0. Notice it's not y is greater than or equal to 0 because the line will never touch 0. It approaches 0 but never touches it. That's what the asymptote is. So the range here is y is greater than 0. Okay, so let's get into doing an example here, and we're going to do this fairly straightforward. So this first one, we're going to make a table. So with y equals 4 to the x, again, we could use our little method that we use over to the left there, knowing what our starting point is going to be, but we're just going to show you. So we're going to do x is -2. If you plug 4 to the -2, that would be like saying 1 over 4 squared, which would be 1 over 16. So that means we have 1/16. If we put -1 in for our exponent, that's going to be 1 over 4. If we put in 0, we're going to get 1. If we put in 1, we're going to get 4. And if we put in 2, we're going to get 16. And again, all I'm doing is plugging these x values in for my x up here. So what we can do is we can actually plug these values in. And again, it's going to be pretty tough to get 1/16 exactly, but we're going to do our best. So that's 1 point. That's our next point. Then we have our 0, 1. Then we have our 1, 4. And then our 2, 16 is going to be somewhere way up here. So when we graph this, again, we're going to draw our line. It never touches the x-axis. So we're going to do the best that we can here to draw a smooth curve. I didn't do a great job, but that's okay. That's the general idea of what an exponential function looks like. Okay, the domain here, as we've already said, is all real numbers. In our range, again, that's our y values. So you can see we start at 0, but we're not hitting 0. So we're just going to say y is greater than 0. So based on this is our parent function. So our parent function is y equals b to the x. So y equals 4 to the x is a parent function. Y equals 6 to the x is still a parent function. Okay, it's what we do in front of the 4 and what we do up in the exponent and after it, that's what can change it, and we will see that. So it says the graph of the function y equals a times b to the x is either going to be a vertical stretch or a shrink of the graph of y equals b to the x. So as soon as we put a number in front of the b, that is where we're going to have an issue. That's where it's going to either stretch it or shrink it. The y-intercept of the graph y equals a times b to the x occurs at 0, a. Rather than 0, 1. So what you see is we have 0, 1 is our y equals b to the x. But if we put an a in front, our new intercept is going to be 0, a. So it'll be whatever number's in front of that b. Okay, and then translations, remember we talked about translations, how they work the same for everything. So you can see this is a times b to the x minus h. So that minus h is up in the exponent. That is our horizontal shift, what we move left and right. And then our k is our vertical shift, that's where we move up and down. And then that h is going to work the same way. If it's minus is part of the equation, so whatever you have, it's going to be moved in the opposite direction. So let's just go and look at a couple of these, how they change. So basically what we're looking at here is we have 1/2 times 3 to the x. What that means is that our 3 to the x would be our parent graph. Okay, so our parent graph would still start at 0, 1, and then we would be at 1, 3. So that's our first graph. That would just be y equals, and what I'm going to do here actually is we're going to zoom in on this. So let's zoom in. So that way we can get a better look. Okay, so when we graph this, if I graph my parent function, it's going to be, I'm going to have a point at 1, and I'm going to have a point at 3, at 1, 3, because it's 3 to the x. And our graph looks something like this. So that's our parent function, just y equals 3 to the x. Okay, now I'm going to do our new one. Well, now what we've said is that our y-intercept will change to whatever our a value is. So now it's going to be 1/2. And then the other thing is that 1/2 is going to literally take this 3 in half. So now it's going to be 1.5. So we have our 2 points there. And again, our asymptote is still going to be the x-axis because we have not changed anything. So this one, it's basically the same shape of the graph, but it goes up a little bit less steep. But other than that, it still looks exactly the same. So for this one, our domain and range, our domain is still going to be all real numbers as always, because every x value is valid. And our range, because we did not move it, it's still, we didn't move it up or down, so it's still going to be y is greater than 0. Okay, moving over to this one. Okay, this is going to be a little bit different. So this again, 3 to the x is still our parent function. So let me graph that real quick. So 3 to the x, that's our parent function. That's what we're going to graph. That's our x. That's the one that's going to be in black here. So we have our 1, and then we have our 1, 3. Okay, same thing as before. We graph this. Our asymptote is still the x-axis. Okay, so there's that graph. So now let's talk about this one. So here we have x plus 1. So that plus 1 means that we're going to shift everything to the left 1 value, and that plus 2 means that we're going to shift everything up 2 values. So our new points, and we can do this with both of these, left 1, up 2. left 1, up 2. Now the thing is that our asymptote will always be determined by this value right here. Over on the original one, we didn't have a plus k at the end. There was nothing at the end. That's why it ends up being 0. Over here on the right, it ends up being plus 2. Therefore, our asymptote is now going to be at 2. But the point is the graph should look exactly the same. It's just shifted a little bit. So it looks exactly the same. The reason why all these points are able to stay the same and we're only shifting them to those spots is because there was nothing in front of the 3. If there was a 2 in front of the 3, then these points would have to shift a little bit. They would be, this one would be double of where it originally was. So you do a parent graph, and then you would see what happens based on the number in front. And again, you can always use your calculator to look at this, but we're trying to get you comfortable with at least shifting these around and knowing what the basic shape of these are. Okay, so this is all exponential growth. Domain, all real numbers again. Okay, but our range is now going to change because now we're starting at 2. So it's going to be y is greater than 2. It never touches 2. That's our asymptote. So it approaches 2 but never touches it. And that's all based on this value right here. Okay? So let's move on to the next thing. All right, so the next thing that we're talking about is exponential growth models. So this is actually where it's really, this is where it involves real life type quantities. So when a real life quantity increases by a fixed % each year, we call that a growth model. Okay, so this is the equation that we use, and A will be your initial amount. So this is the initial amount that we have. R is going to be the % increase represented as a decimal. So if I give you 45%, then that means we're going to get 0.45, and then that's going to be added to 1. The T is going to be the amount of time in years, and then we call the 1 plus R, so when you combine that, that's called your growth factor. So all I want to talk about here in this example is just identifying what each of these pieces are in this equation. So we want to identify what our initial amount is. So our initial amount, and I'm just going to write it right on top of here. Okay, the initial amount is 527. That's the value that's out in front. The growth factor, that is the entire part inside the parentheses. That is 1.39. And the % increase only is the 0.39, but you need to turn it back into a percentage, so the % increase is 39%. So 527 your initial amount, 1.39 is your growth factor, and the % increase is 39%. So now let's talk about how we really apply this, and that's in the case of compound interest. So this is like if you were to put money into an account, we would be able to figure out what, how much we would have left at the end. So let me rezoom this a little bit here. Okay, so the compound interest says that it's pretty much the same as before, but we have different letters. P is the principal. That's the amount that's deposited in the account. R is going to be the percentage rate that we're getting. N is going to be the number of times that that rate is accrued annually. And then N is going to be, again, the number of times that it's compounded annually, and T is going to be the number of years. So the reason why this N is important is because a percentage rate is not always annual. In this case right here, we're saying it's quarterly, which means 4 times per year. So when we write out our equation here, it's going to look like A equals 2,000, that's our initial amount, in parentheses is 1 plus. Now, our percentage rate is 4%, so it's 0.04. And because it's quarterly, we have to divide that by 4. That's what our N comes in. And we're going to do it for 3 years, but we have to multiply it by our N. So it's 4 times 3, which is 12. So basically, all this is just a formula that you're plugging values into. Principal into the principal, percentage rate into the rate as a decimal, N is going to be the number of times per year, and then T is going to be the number of years. And literally, you can just take this value right here, this equation, plug it right into a calculator and get your answer. And I've already done that ahead of time, and we would get, after 3 years, $2,253.65. And I'm out of time, so I'll see you guys tomorrow. Take care.